Okay, so as promised last week, on Thursday, I set up and solved a game for you. We talked about it a little bit, but as I said on Thursday, I didn't say all I wanted to say about that game, and indeed you might not have had the opportunity to say all you want to say about the game. So I'm going to just put it up very quickly, go through it more quickly than we did on Thursday, and then I'll be jumping in to first start off with some observations about payoffs. Okay, but just to refresh your memories, this game has two players, an incumbent member of Congress and a challenger. They're both deciding whether to raise funds or not. They both want to win the election. Only one of them can. They both don't like fundraising either. Okay. The game had a sequence to it, so we represented it with a game tree with the first mover's decision depicted at the top decision node. I'm trying my best to use all those vocabulary terms I was throwing at you on Thursday. The incumbent's decision node has a branch for each possible action the incumbent can take, and we were simplifying the situation a lot. We said the incumbent's choice was just raise funds or not. I'm abbreviating. And then whatever the incumbent did, the challenger got to react. Okay, so the challenger has two decision nodes, but again, I'll emphasize that only one of these is going to happen. Okay, either we're going to go down this path of the tree, the incumbent raises funds, and the challenger is then going to decide whether she wants to raise funds or not, or we're going to go down this branch of the tree. Okay, so the challenger has two possible decisions that she will have to make, but only one of them is actually going to appear in reality. Only one branch is going to be taken. Okay. We set up the tree in the natural sequence with the thing that happens first at the top and later decisions coming lower in the tree. At the very bottom of the tree, we put the terminal nodes, and what's in the terminal nodes are the payoffs. Okay. We put numbers, one for each player, that indicates how well they like the outcome associated with this particular set of decisions by all players. Okay. Thursday we spent a lot of time talking about the outcomes, talking about what would happen in the case that both candidates raised funds, what would happen if just the incumbent did, if just the challenger did, neither did. We spent a lot of time on me explaining my assumptions to you about the outcomes, but as I said, the outcomes don't appear directly in the tree. We need to think about them in order to put the payoffs in the tree, and I'm going to, as I'm talking, just put in those payoff numbers that we had last time, but the outcomes don't actually occur. Okay? We can't, if somebody just walked into the room right now for the first time and looked at the tree on the board, if they knew game theory, they could solve the tree, but they wouldn't necessarily know what it's about. Okay? They would miss that part of it. All right, so the payoffs, first movers pay off first. That's just a convention. You could do it the other way, but people don't. So when in Rome, do as the Romans do. When in game theory, do as the game theorists do. Put the first movers pay off first, and these were the numbers we were using. Okay. The idea of payoffs is very intuitive. It's easy to think of them as points in a game that you might play for fun, and I think nobody was hung up by the idea that players want a higher payoff, and in solving the game, the way we solved it, working from the bottom up, was for each decision node to ask which branch would give the player who controlled the decision node the higher payoff. Okay? So using that idea, if we get to this node, the challenger compares her payoff from raising funds to her payoff from not raising funds. And I really want to emphasize that we're always comparing payoffs that belong to the same player. Okay, we're comparing the challenger's payoff for one outcome to the challenger's payoff for another. Okay, so this is a challenger payoff from what I'm going to abbreviate, raise funds, raise funds. Okay, incumbent raises funds, challenger raises funds. This is the challenger payoff from the outcome raise funds not. Okay, raise funds not. We're comparing challenger to challenger. Never in game theory do we need to compare one player's payoff to another player's payoff. We never do that. If you find yourself doing that, pinch yourself. You're doing something wrong. Okay? We only compare payoffs for the same player. Okay? I'm getting a little ahead in my outline, but I think this is something I'm probably going to emphasize more than once. We don't make interpersonal comparisons of payoffs. Okay? It's very taboo to do that. And the reason why is this idea of payoffs, you may or may not find it a reasonable way to represent people's payoffs. I'll talk about how reasonable it is, when it might not be reasonable later on. Okay? But it's much more reasonable to think that I, as one person, can give a higher or lower number to different things that I could experience in a way that would reflect my preferences, than to think that I can compare how much it means to me to avoid fundraising versus how much it means to you to avoid fundraising. Okay? We can't compare my happiness, my utility, to somebody else's utility. One way to see this is to sort of back off from this idea of payoffs and link them to a broader concept, the concept that if you've taken any economics classes, I'm sure you've heard the word utility. What we're doing with payoffs is exactly the same thought experiment that the exact same useful fiction that we do in microeconomics when we use utility. It's the same idea, a number that represents how good you feel about something. In economics, the utility numbers are often assigned to how good you feel about something you can buy. Do you get a higher utility from spending all your money going out to dinner and having a small apartment, or would you rather have a big apartment and stay home and cook your dinners? That's the kind of scenario that you may have encountered in a microeconomics class. Here, we're more interested in assigning utility to political situations, but it's the same idea. It's a very old idea. The term utility is usually associated with Jeremy Bentham, a major philosopher, wrote in the, I guess, late 18th century. I don't actually know that he coined the term utility, but he certainly popularized it, and the use that we make of it today owes much to Bentham. One way that people often understand the concept of utility is that it gives us a way to compare apples and oranges. That's the cliche. Okay? And you may have heard this cliche expressed the other way. People tend to say that if they don't know how to make a choice or they're uncomfortable with the choice that they have to make, they'll say, well, is this a better apple than that is an orange? I don't know. You can't make that comparison. Okay, so in one sense, you can't make that comparison in a global sense of what is the perfect apple, what is the perfect orange. We don't need to do there. What you can say, though, what we do all the time, we could not get through the day without making comparisons of, do I want an apple now, do I want an orange now? Do I want to speed up and go through the yellow, or do I want to stop? I mean, we're just constantly comparing situations that are different, and the idea of a utility function, the idea of assigning utility numbers to different things that can happen, is just a way for us to organize what we think ourselves are doing when we're making comparisons and making choices based on those comparisons all the time. It's a way to think about what we are doing ourselves. It's also, and for this class more important, a way for us to talk about what we think other people are doing. Okay, so when we're doing social science, we're constantly talking about what other people are doing, and as I tried to emphasize last week, we need to be thinking about what our assumptions are about the people we're trying to understand's preferences. Okay, utility numbers are the conventional way in economics, in game theory, in decision theory, in management science. It's used sort of throughout the social sciences, the conventional way to understand people's preferences, to understand how people make choices, choices that involve comparing apples and oranges, comparing non-alike things. Okay, and so I hope you can kind of see how the utility idea gives us a way to compare apples and oranges. If the comparison is apples to apples and say it's quantity, do I want 3 apples or 1 apple? Let's say I like apples, I'll choose 3. That's easy. I don't need utility for that. I can just count apples. Do I choose 1 apple or 1 orange? No, I don't know what I'm going to do because they're different things. If I map both of those things, apple and oranges, into the same thing, into a number, I can compare numbers. Okay? So by assigning numbers to every possible thing, we can compare numbers. That's the idea. Let me emphasize again, I feel like I can't emphasize enough. Nobody thinks utility is real, okay? We don't even think it's something that, these days they could do an MRI and see what part of your brains are lighting up and measure how much dopamine you have floating around in your brain that may, and some of those things may indeed give us some insight to how good the person is feeling at a particular point in time. That's not what we think utility is. Okay? Utility is a useful fiction. We don't think it's real. It just is a way of helping us talk sensibly and coherently about preferences. And we do, and game theory is based on the idea that preferences are real. Not that they're always stable, but there's enough reality to preferences that we need to think about them to understand how people behave and to understand how people interact. Okay? So the fiction is useful. It's tolerable to think that an individual person can compare apples and oranges. I think it's completely reasonable to assume that. It's unreasonable to say the enjoyment I get from an apple is more than the enjoyment you get from an apple. We just can't know that. Okay. Now, if you were taking an analytic philosophy course, there are courses in the philosophy department that deal with issues involving utility and that actually deal with some issues in game theory as well. That question of interpersonal comparisons would be on the table. Okay, so maybe I shouldn't come on too strong and say that we absolutely can't do it. What is a more reasonable thing for me to say, a more judicious thing for me to say, is that in game theory we don't have to do it. It's much, much dicier to think that we can compare one person's preferences to another, and the nice thing is that in game theory we just don't have to. So that's very good. Okay. That's what I wanted to say about interpersonal comparisons. I think some of why you might care about interpersonal comparisons, why you might be tempted to make them, will be clearer once you start working on your homework problem. Okay, so take-home message here is never, never compare one person's payoff to another person's payoff. Okay, it doesn't make sense. It's not part of the standard utility thought experiment. The other thing I wanted to say about utilities, about these payoff numbers is I was gliding over them a little bit quickly on Tuesday, and something that I said is that the numbers represent the order of preference. I think I very glibly said what you get from the utility number is high number good, low number bad. And that's true. You do get that, but you get a little bit more. Okay? The utility numbers for a person represent not only the order of preference. Okay, it's not just the higher number is better for the person, but it also represents the person's intensity of preference. So over here, let me just summarize the assumptions I'd made about the preferences for both candidates. Okay, I'd written it separately on Thursday, but there was a clear parallel. Both candidates, we said, got a payoff of 10 from the outcome of where they win the election, no fundraising. Okay? Implicit in this little box of payoffs that I'm going to put up here is that they care about whether they win, and 2, they care about their own fundraising. Okay? So if I'm the incumbent, I'd prefer that I don't raise funds, but I don't care if you do. Challenger, I care about whether the challenger raises funds, don't care about whether the incumbent does. The other possible outcomes, now I've got both candidates together, so actually all of these is going to be possible for at least one player. Winning with raising funds was worth 8. Losing no fundraising was worth 3. And losing raising funds, that was the worst outcome. We said that was worth 1. Okay, so just as I wrote it up there, it's from best outcome to worst outcome. But in passing, what I mentioned was you could think about these numbers as capturing 2 independent aspects of the situation. The way I set it up, there are 2 independent aspects. Okay, so that winning is worth 7 points. Okay. How do I know? If I hold the fundraising constant, the difference between winning and losing is 10 minus 3, that's 7, or 8 minus 1, that's also 7. Okay. Raising funds, we could say, is worth, what's raising funds worth to my utility? It's worth 2. How about negative 2? Right? The way I wrote it here, if I said not raising funds, that would be 2, but raising funds costs you 2. And I'm emphasizing this, what seems to be a minor point of language, because you're going to have to deal with these negative numbers in this problem set and all of the problem sets you get. Okay? More so than in economic applications of utility theory, in political science, good things happen and bad things happen. Okay, it's not just giving up money to get stuff that is good. It's making choices that bring about good consequences, that bring about bad consequences. So when we are putting together the composite numbers that represent our net payoff from whatever outcome we're studying, we have to remember that good things increase our utility, bad things decrease them. Okay. Another way to think about this is when you're reading your problem set, I'm pretty sure I used the word cost at some point in that. If I didn't in this problem set, I'm sure I will in a future one. Another way we could just say the same thing is that raising funds costs 2 units of utility. Okay. It might seem obvious, but every year people get confused with dealing with aspects of choices that cost the players some utility. If it costs the players some utility, it means you subtract that amount of utility. Okay? So if this was a problem set, and I was giving you a scenario analogous to the one that I have given you today, I might actually write something like what I just said. Each player values winning at 7 points. Each player dislikes fundraising, and that costs the player 2 units of utility. Okay, that's the way to take that kind of ordinary language and translate it into a game. Okay. Again, I said this on Thursday, but I think I said it really quickly. If we think about winning is worth 7 points and fundraising worth -2 points, utility units, whatever you want to call it, there's sort of an implied baseline here. What's your payoff when you don't win and you don't raise funds? It's up there. 3. Okay. Baseline in this problem is 3. Okay. I think I sort of flippantly said that 3 was the value of a day job outside of politics. Okay. Not being in office, but not raising funds either. Most of the time, we will use a baseline of 0. Okay, we get to pick what our baseline is. Okay. When I set up this example, I deliberately didn't pick a baseline of 0 because what I want to show you, and I think I will show you explicitly in just a second, is that it doesn't matter. Okay, but usually having some kind of neutral outcome associated with payoffs, with a baseline payoffs, make it easy for yourself. Make it 0. Yes? The baseline, the question is, what's your name? Neve asked whether the baseline is when you don't have any costs, you don't have any benefits. That is a natural one to choose as a baseline, okay? And you will not go wrong by choosing that. In some scenarios, it's hard to figure out what that should be. What I want to let you know is it doesn't matter. Okay, you could pick any one of these outcomes as the baseline, and you would get different numbers to represent the utility. Okay, so for example, if we said, I'm going to let the best possible outcome be 100, and well, that's pretty close to 10. You can just multiply everything. I'm going to let the best possible outcome be 5 and make everything else relative to that, or like the best possible outcome be 0 and have all the other numbers be negative. As long as the relationship between the numbers is the same, I'll get the same answer in the game. And if you think about what I did to solve the game, of course that makes sense. I'm just comparing the numbers here. So you can A, pick any outcome as your baseline. B, you can pick any numbers you want. I could pick these numbers. It wouldn't change it. I could pick 1.8, 0.3, 0.1. That wouldn't change it. I actually have a great deal of freedom in picking my numbers. What we are going to see probably by the end of the week is that most of the time in social science when we do game theory, we don't actually use numbers, we use variables, and the variables will allow us to do a little bit more. Okay, and those variables are sensitive to the fact that the numbers themselves don't matter as much as the relationship between them. Yes, Elaine?
What is your baseline supposed to represent?
The baseline is, so let me step back and say the baseline is not part of the game. You could think of it as a stepping stone between the story in ordinary language and the game. And something that you'll be doing in your homework, something I'm going to be doing for you throughout this class, is explaining the logic of how you go from the story to the game. That's an important part of knowing how to do game theory. And it's actually, let me step back and say, it's something you want to do in your homeworks. Okay? The homeworks will say, write down the game tree. And yes, you should write down the game tree, but it's actually a good idea to write a little paragraph explaining how you're setting up the game tree. That kind of support statement is part of using game theory to say something about politics. Picking a baseline outcome is a good way to explain why you're setting up the game the way you do. And in many contexts, the baseline will sort of be natural, like most people would think that that would be a natural one. It's actually not clear to me that this has a natural baseline. The losing without raising funds, you could sort of see that, but I could also see a logic of maybe picking this as a baseline and having everything be relative to it. Neve suggests, and I think it's a good idea, that if the game has kind of a status quo, okay, it's about this is what happens if nobody does anything, and here's different ways that people can change it and then react to what another player does, that status quo is often a natural thing to use as a baseline. Okay? Okay. I'm going to leave these numbers here, and let's see how it's probably not such a good color. Let's use blue here. Another possibility would be just to take the advice that I gave you a minute ago. Don't make the baseline 3, make it 0. Remember, I'm making these numbers up. They're just designed to convey my ideas so I can pick a number, and 0 is actually a nicer number. I'm going to leave these other two numbers alone. That winning is worth 7 points and raising funds gives me -2. Okay, so now I've got a different set of payoffs. Okay, my baseline here is 0 now. Okay, if going from that baseline I win and I don't raise funds, what's that going to give me for a payoff? 7, okay? If going from this baseline of 0, I win, but I have to raise funds, what's my payoff? 5, okay? If going from this baseline, I raise funds and I lose, what do I get? -2, okay? So all fine. This is actually a good example because one thing it illustrates is that nothing special about negative numbers. Just treat them the same. Let's put those alternate payoffs here in the game. That doesn't look alternate. That looks the same. My alternate payoffs here would be in this situation. The incumbent's payoff is I won, I raised funds. It's a 5. What's the challenger's payoff? What is it? -2. Very good. Okay. Incumbent's payoff here? 5, right? Incumbent raised funds here. Okay. What's the challenger's payoff here? 0. There's my baseline. Incumbent's payoff here? Yeah. Challenger's payoff? 5. Incumbent's payoff here? There's that 7. There's that lovely payoff, and right here, baseline again. Okay. So it's a different game now. Instead of the game with the black payoffs, it's the game with the blue payoffs. But if we solve it the same way, we do the same algorithm. Let's just do it now. I'm the challenger here. If I get to this node, would I rather have a payoff of -2 or 0? I'll take the 0. Thank you. 0 is nothing, but at least it's not negative. So I will not raise funds. If we get to this point in the game, we go down this path in the tree. I'm the challenger. I'm comparing 5 to 0. 5 is good. I'll take that. don't know if you want to say halfway, 2/3 of the way through solving the game right now. I've decided what I'm going to do at each of these nodes. Now I replace these decision nodes with the strategic equivalent. The strategic equivalent of this decision node is the payoffs associated with the optimal choice at this node. The optimal choice at this node for the challenger is no. The payoffs associated with that choice are 8-3. Okay? What's a little bit tricky here is that the strategic equivalent has a payoff for both players, but the reason why this is the strategic equivalent and not that is only based on the challenger's choice. Okay? So I've just pruned this whole part of the tree. I don't have to think about it anymore. All I need to know about this node is that the strategic equivalent is 8-3. Over here, all I need to know is that the strategic equivalent is 0-5. Yes? The reason is, okay, I'm even early today. I'm starting to make those mistakes. Bless your heart. Okay, I did it right here, okay? It's, I was pointing to the right place, but right now, green, let me emphasize this, green is supposed to be solving the blue payoff game, okay? And the blue payoff game doesn't have these payoffs in it. The strategic equivalent is 5-0, okay? Yeah. Oh, that's a particularly pernicious mistake because I think I would have gotten the right answer anyway, and those are the worst. The ones where I get the wrong answer, I can usually correct myself, so thank you. Okay, so strategic equivalent now of both of those nodes. Final step in solving the game, back up a level to this decision node. The incumbent looks at the two choices and at the strategic equivalent associated with it. Okay, this is the key ingredient in thinking strategically. The incumbent does not look at raise funds or not and say, oh, raising funds cost me 2 units of utility. Doing that would be wrong. It would be not strategic. When we use game theory to understand politics, we assume that people are too smart to do that. Okay? We assume that the incumbent will say, raising funds is a pain in the short run, but it is the equivalent of a payoff of 5. Not raising funds is nice in the short run, but if I don't do it, if I anticipate what my challenger is going to do, I'm going to get a payoff of 0. Okay? So this, by replacing this row of decision nodes with the strategic equivalents, I can solve the higher node. If it was a game with even more nodes, then I would replace this decision node with its strategic equivalent. This 5-0 would bump up even higher, and I would just do that till I got to the very top of the tree. Okay. Now the point of this example was to emphasize that we get the same result when we use different numbers. Okay, so I hope that that part came through clearly here. Okay. All right, I think I'm just going to leave the game with kind of the double set of payoffs here. And let me kind of catch my breath a second and emphasize 2 basic points. Okay, one basic point is that by solving the game, we get a prediction about what's going to happen. Okay, we predict that the incumbent is going to raise funds, the challenger is not going to raise funds. Okay, so one thing we get from a game is a prediction about what the players are going to do. And sometimes that is indeed what we use game theory for. Okay, that use of game theory is it's used practically in what's sometimes called questions of institutional design. Okay? If you don't like what's happening in a situation, if you're the professor and you don't like the way the students are performing, you might redesign the one institution you can control, which is the syllabus. Okay? And if you're a game theory professor, you think strategically when you do that and try to put you guys in a position where your optimal choice will be the one that's going to make you learn the most. In more serious situations, if you are the United Nations and you are sending blue helmets to a country whose people are killing each other, and you're trying to figure out some way to rearrange how people move about, how people trade with each other, how people make their livings, so that there's not such an incentive for violence and crime. This happens in a wide variety of situations. You might actually use game trees, try to figure out what people's preferences are. That's always a key component of it. But then figure out how they would respond to different types of choices. And sometimes you're in a position where you can change the choices that are available to people, or you're part of a conversation, more likely, where a group of interested parties are trying to change the choices people can make and how those choices add up to outcomes in a way that would make everybody better off. And in that case, using a game to figure out what the outcome would be helpful. So I don't want to denigrate that fact that the game gives us a prediction. It's not worth a whole lot in this particular context because we started with the observation that this is what happens. Okay? I didn't need game theory when I first told you this little puzzle on Thursday that incumbents raise funds so insatiably, even though their challengers don't seem to do much and they always win anyway. So we didn't need the game to tell us that incumbents would raise a lot of funds and that often challengers would not. What we were looking for was an explanation for why. Okay, and that's something else we get from game theory. We get an understanding of why the predicted outcome occurs. More important, that understanding of why the predicted outcome occurs always depends on the outcome that didn't occur. Okay? I've been emphasizing this all along, and I will continue to because I think it's one of the most important lessons from game theory. If we want to understand what is going on in the world, if we want to understand why it's going on, we have to ask ourselves, what else could have happened and why not? Okay? What that means, whenever we're analyzing a game, we're not just satisfied with predicting what's going to happen. We also want to make sure and say something about what we think would happen in the counterfactual. Okay? That's key to the logic of game theory. Okay? May not get to the full explanation of this today, but we're going to be developing this idea of an equilibrium. Okay? A situation where neither player by themselves can improve by making a different choice. Given that the incumbent has raised funds, the challenger is not going to do better by making different choices than she did. And given that the challenger's decision is to raise funds if the incumbent doesn't, and not raise funds if she does, there's nothing the incumbent can do that would bring about a better outcome. Okay? The idea of equilibrium brings with it an idea of what we'll call the equilibrium path. The equilibrium path, I'll write it over here. What we expect at each decision node. Okay? Another phrase for this is, well, the predicted outcome. Okay? What do we think the guys are going to do? What do we think we're going to see in this situation? This. But just as important is what's going on off the equilibrium path. What's going on off the equilibrium path over here is what helps us understand why. Okay. All right. So I want to say some things about, I'm going to add some more vocabulary terms here that are going to help us manage this counterfactual part of the solution of the game. Okay, this idea that when we understand a strategic situation, we not only understand what's happening on the equilibrium path, but what's happening off the equilibrium path. And the reason why we need to know what's going on what would be going on off the equilibrium path is that that's the reason why we do observe what we do. Okay? All right. So on that, I'm not going to use green. That's not a good one. What's this? Okay. All right. So I think I will just put some, a couple of definitions here. First of all, I'm going to make a distinction between strategies and actions. In ordinary language, those two things could mean the same thing in this context. What's your strategy? What are you going to choose? They almost seem synonymous. In game theory, a strategy is a more complicated thing than an action. Okay, so let's say why. Okay, so they like mine this tray with these fake markers that don't work. An action is a choice at a node. Okay, so an action is a really simple thing. An action corresponds to one branch. Okay, so this is a decision node with two possible actions. Here's another one with two possible actions. At some point, we'll probably do an example where the decision maker has three possible actions at one node. Guess what? They choose the highest payoff of the three or the four or however many. Nothing too strange about that. But an action is just this one simple choice, one branch in a tree. A strategy is composed of actions. Okay? So I'm going to do this definition in more of a complete sentence. A player's strategy is an action for each node she controls in the game. Okay. All right, so let's go back to the black payoffs. Now I'm going to get rid of the blue ones, and let's use this board space here to talk about strategies. And what is an example of a strategy for the challenger? What would be a strategy for the challenger? I know people don't know how to put it in words. I think you know it. What would be an example of a strategy for the incumbent? Raise funds. Okay. The incumbent only has two possible strategies in this game: raise funds or not. For the incumbent, there's no difference between a strategy and an action because the incumbent only controls one decision node. Okay. Let me put it, the question to you in a little more precise term. The challenger has some strategies in this game. What's the challenger's best strategy? What's the strategy we think the challenger is going to play? Say it louder. Raise funds. Is that a full strategy? When incumbent does not, and not when incumbent does. The challenger's strategy is more of a mouthful. That's why it was kind of unfair for me to ask you guys to say it, because I've been usually asking you things that you can answer with one word. Okay? This is one of the challenger's 4 possible strategies. Okay? I'm going to write down another one, and I'm going to use a kind of shorthand that you're going to find very useful for your homeworks. Okay? Another possible strategy that the fundraiser has is RF, if RF, RF, if N. Okay, so I'm using shorthand here. Another strategy that the challenger has, it's not the challenger's best strategy, but it's a possible strategy, is to raise funds if the incumbent raises funds, and to raise funds if he doesn't. Okay, challenger could just be a fundraising energizer bunny. It's a strategy. Like I'm saying, not the best one, not as good as this, but it's a possibility. Okay, another even shorter way to abbreviate it. Okay, so one way to abbreviate, and this is actually the way I like to do it, and I would encourage you to do it this way on your homeworks and even more so on your exam. Because this way, to me, is still staying in touch with the story here. Okay, I raise funds if the incumbent raises funds. I raise funds if the incumbent doesn't. I'm saying especially on the test, because on the tests, especially on the midterm, you know, we only have an hour and 15 minutes here. You guys are going to be pressed for time, and you're going to think, I just got to write as fast as possible. And so you're going to be tempted to use the form that they use in the book, and let me just show you what it is. So another possibility would be to raise funds if the incumbent does not raise funds. Okay? This is the most terse abbreviation of the challenger's strategy, and let me decode it for you. Okay, so this is action at, not right, left. Leftmost node, action at next node. Okay? In coming up with a strategy for a player that's a second mover or a third mover, what you're going to do is you're going to go across this row of decision nodes that is controlled by the challenger, and you're going to list all the combinations of actions at those nodes. And one way to do it would just be to say a strategy is raise funds here, not here. Raise funds here, raise funds here. Not here, not here. Not raise funds here, raise funds here. I think those were the 4 there. I don't want to say this is wrong. People definitely do it, but what I will say is that if you're doing it too fast on an exam, even though it seems like you're saving time, if you get confused, you get to an answer that doesn't make sense, you want to go back and check your work, you're more likely to understand what's going on in the game if you have it set up like that. This is just going to look like symbols. Okay, so this is my preferred way to denote a strategy. When you see people denoting strategies just by a string of actions, the way to interpret it is that it's the action associated with the leftmost node first and the rightmost node second, in this case, where there's just 2. If there was a third decision node over here, we'd have to have 3 actions. Okay. Okay, challenger has one more strategy. What's the challenger's other strategy? Don't raise funds no matter what. That's exactly right. Okay, so number 4 is N if RF and if N. Okay. For both of these abbreviations, what you want to be thinking of is that for each decision node that the player has, you're going to have that many strings, that many things strung together by commas. Okay? Strategies by themselves really is all you, actions by themselves is really all you need to have the full strategy. It's just a little helpful, I think, to have this level of background information in there. Okay. All right. So relationship 1 is strategies versus actions. Okay? So actions are like our atoms. They're the smallest thing, they're one branch in a node. Strategies are combinations of actions. Sometimes a strategy is simple, as in the case with the incumbent. Sometimes the strategies are a little more complicated. If you get big game trees with lots of decision nodes, just writing down the strategies can be a challenge. Okay. Thankfully, we can do a lot of analysis. I think we can actually get more insight from small games with few decision nodes than big, hairy games with 1 million decision nodes. Okay. Strategies, more complicated than actions. And then the next step up is equilibria are more complicated than strategies. Okay, so let me, actually I think I want to leave this, and I've already started writing some stuff about equilibrium over here, so let's get the full definition here. Okay. Equilibrium is a strategy for each player such that neither player could do better given the other players, apostrophe could be here or could be here, however many players there are, one other, many other strategies. Okay? So we're building up. Action is composed of nothing. Action is just an action. A strategy is composed of actions, and when I wrote the definition of a strategy, I had to specify that a strategy belonged to a player. Okay? So when you say, what's a strategy, you have to single out one player to pick a strategy. Equilibrium is made of strategies, one for each player. Okay? Strategy, action for each node, equilibrium, strategy for each player. Components are simple, but they build up. It's not just any old strategies, though. If the strategy set that composes the equilibrium is really an equilibrium, it means that neither player can change, neither player can do better by changing unless the other player changes. Okay? So if you keep on doing your thing, you're the challenger, I'm the incumbent, if you're playing this green strategy here, okay? If you're going to not raise funds when I do, but raise funds if I don't, then I can't do better by not raising funds. Okay? Similarly, if I'm the challenger and the incumbent is going to raise funds, I can't do better by changing my strategy either. Okay? There's nothing I can do if the incumbent is going to raise funds. There's nothing I can do to get myself a higher payoff. Okay? The challenger's part of the equilibrium analysis is kind of obvious because it was part of solving the game. We kind of have to step back to see the incumbents part of that. That given the challenger's full strategy, the incumbent cannot do better by changing. Okay? And again, that's how we're getting this explanation of why things are the way they are from the game. Okay? After class on Thursday, I got a question that sort of pointed to this 10 payoff over here. Okay? Great payoff, right? Why can't the incumbent get to that payoff? Because of the strategy that the challenger is playing. Okay? In one sense, the incumbent can do better in this game than the outcome we're predicting. The incumbent could get a 10, but not when the challenger is playing this strategy. Okay? That's why the incumbent's choice is equilibrium. Okay? So, let me write the punchline here. Equilibrium in this game is incumbent, raise funds, challenger, not if incumbent raises funds, but raise funds if not. Okay. On your homeworks, on the exams, in any application of game theory, anytime somebody asks you what the equilibrium in a sequential game is, this is the kind of thing they're looking for. They're looking for a pair of strategies for each player. And each strategy, I'm going to give the definition in a different, slightly different language. Each strategy is a best response to the others. Okay, my strategy is a best response to your strategy is a best response to my strategy. Our choices reinforce each other. Okay? You're the incumbent. Given what you did, I'm the challenger. I'm glad I didn't raise funds. It's a little bit harder to see from the incumbent's side, though, but now we're able to see it. If I'm the incumbent, given that this is your whole strategy, including the off-the-equilibrium path part of your strategy, given what you did and what you would do, I don't regret what I did. Okay? So the second mover strategy has to be both what they do in equilibrium and what they would do otherwise. Because what they would do otherwise is often the reason why the first mover makes the choice that she does. Okay? So let me just emphasize that this is just a restated definition of equilibrium. Okay? Same idea, just in different words. Okay? Another thing, another vocabulary thing I want to alert you to is the book calls this rollback equilibrium. What we do when we solve the game with the rollback process is we find the equilibrium. That's been at the core of everything that we've done so far. Okay? Rollback, later in the course we'll start to talk about what that means. Right now, rollback is the only kind of equilibrium we know about. Okay? So just sit tight with that. When we do the rollback process, what we get are the strategies in a sequential game that satisfy this idea of equilibrium. Okay? What makes rollback special is that it only applies to games where first one player moves and then another player moves. What we're going to be getting to in probably the second 2/3 of the class is the same idea of equilibrium, but in cases where the players make their choices at the same time. Those are a little bit harder. Okay. Let's see what else I have. All right. Yeah. I want to do one last thing, and I think we've just got the right amount of time to do it. This difference between strategies and actions, that an action is a simple thing, strategies are composed of actions, strategies are more complicated things. You guys are all nodding right now. I know you get it right now. I know some of you are going to lose it. I don't understand why it's slippery, but it is slippery. It's not the natural way we think about strategy. So just to maybe juxtapose that, in ordinary language, if this is Challenger, you're working for this Challenger, or you're a journalist interviewing them, and you say, what's your fundraising strategy? In ordinary language, the Challenger could either give a game theoretic definition of the strategy. In ordinary language, the Challenger might say, well, my strategy is if the incumbent raised funds, I won't. If the incumbent didn't, I will. But more likely, especially if we already know what the incumbent's going to do, if you asked the Challenger what his strategy is going to be, he would say, so he wouldn't necessarily just say, I'm not going to fundraise. He'd say, I'm above money politics, so I'm going to rely on the strength of my ideas and my grassroots support. But you'd know what his strategy was. But more importantly, that ordinary language response that he would give would just be an action. Okay, so in ordinary language in the newspaper, when we talk about strategy in politics, I think it's also true when we talk about strategy in games and sports as well, that a full strategy in a football game or something like that would have branches in the trees. What are we going to do if they do this? What are we going to do if they do that? But in the middle of the game, what's our strategy going to be on this play? The ordinary language answer to that would be more like an action. Okay. So because keeping the distinction between strategy and action distinct is a little tricky. It's unusual for us. It's doing something that we don't otherwise do. I think on your homework I've asked you to do some strategy counting, and if I haven't, I will. Let's count some strategies in this game. Okay, and this game is going to be kind of quick and dirty here. It's not going to have a story. We're just going to have player one here. Player one has 3 possible actions. Okay, they are left, middle, and right. How interesting is this story? Once player one makes a choice, player two makes a choice. Player two, regardless of what player one does, player two can just choose left or right. Left, right. Left, right. Okay. So those are and we're not going to solve this game, so I'm not even going to put payoffs here, but something that you sometimes might want to ask yourself about a game if you're trying to figure out whether you set it up right is to ask yourself how many strategies each player has, okay? Or to enumerate all the strategies just to make sure they're all there. Okay, so player one, how many strategies? Excuse me, question in the back. 3. What are they? Left, middle, and right. Okay. Player one, no problem. Player two. What is one strategy that player two could play? And as much as I don't like this format for writing down, it's okay to call it out as an answer. Okay? L, comma, L. What, actually, say the whole thing. Say the whole thing. Let me.
L, comma, L, and then L, comma, R, or R, comma, L.
Not quite. So you were thinking of L, comma, R? Okay. There are games that would have that, but in this game, we've got player two's decision here, player two's decision here. So here's a strategy, okay? Another one would be L, comma R, comma L. Okay. How about this one? Another one? Okay. Do you guys see what I need to do here? The strategy needs to tell player 2's action for each node. There are 3 possible nodes that player 2 could find herself at. Okay, she could either find herself at the node where player 1 played L, where player 1 played M, or where player 1 played R, and her strategy has to tell her what to do at all 3 of them. Okay? So player 2's strategies have 3 components. Okay? One way that I find helpful and to think about strategies is a strategy is something you could program into a computer. Okay? You know, if you've ever done any programming, the frustrating thing about computers is they have no common sense. They won't see a pattern. You have to tell the computer they have to tell the program what to do for every possibility that can arise. They have no ability to think for themselves. Okay? That's what a strategy does. Okay, a strategy really is something that you could program into a computer. Elaine. Okay, so what I need here, we're going to go back to the definition of the strategy, is an action at each decision node. Okay? Each decision node controlled by player 2. Okay? So again, strategies, whenever we think about strategies, we have to think about which player, okay, because we have to know how many nodes will be included. Okay? Player 2 has, I'm going to use letters here, could be at node A, node B, or node C. If I wasn't already using numbers to represent the players, I'd probably number these, 1, 2, and 3. Not necessarily part of a game, but it helps me remember that all 3 of these nodes belong to player 2. So what I'm doing here is I'm thinking, what is a set of actions for each node? Okay, and the key here is player 2 has 3 nodes. Strategy needs 3 components. Okay. Yes?
Could there be more strategies for player 2?
There are more. There are more. Yeah. Got a candidate for one?
Like
RLR. That's a good one. It's not just those 3. Anybody want to think about how many strategies there are total? Yeah. 8. 8 is right. How'd you get 8? It's 2 to the 3rd power. That's exactly right. The total number of strategies is the number of choices here times the number of choices here times the number of choices here. 2 times 2 times 2. Okay. If we, switching to black here, added medium here. Okay, so now I'm making kind of a very funky game. One can choose left, middle. I guess M is middle, not medium. Sort of the same thing. One can choose left, middle, or right. If one chooses left, can choose left or right. If one chooses middle, two can choose left, middle, or right. And if one chooses right, 2 can choose right or left. Like maybe one choosing middle is actually paving a road that 2 can only walk on if one has already started it. Now what do we have in terms of how many strategies in that game? 12. Okay, because we have 2 times 3 times 2. Okay. The total number of strategies is product across all nodes of the number of actions at each node. Okay. This looks weird, doesn't it? Okay. You'll do a couple of examples. If you feel like you're frustrated with the homework example, one of the first 2 to 3 problems in Dixit and Skeeth, those early problems in the back of the chapter have some strategy counting problems, and I would recommend them. I'm going to recommend some problems in Dixit and Skeeth for you before the midterm anyway, but certainly doesn't hurt to start doing some now. Okay, so stay tuned Thursday. We're not done with this game yet. We're almost done with it, though.